Hi, this lecture is to introduce you to some of the issues that you'll see when you are combining capacitors, right? So the title of this lecture is Capacitor Networks. And by network, I mean various different combinations of capacitors. So combinations of capacitors and capacitor networks indicate the same thing. And there's two generically different sort of basic connections between capacitors. There's the basic connection known as the series connection. And you can see that what's meant by series is, you might imagine this is the beginning of our network, and this is the end of the network. And if you start at the beginning and walk along this wire, this is a wire, you must traverse one of the capacitors before the other. And that's what's meant by series, is that while you go from one end to the other, you have no choice, but in order to get to the second capacitor, you have to sort of imagine walking across the first one. So they come in series. In parallel, this is a generically different situation. So in this case, I drew the beginning and the end going from top to bottom. And really, it doesn't matter. They could be on a diagonal, or, you know, from the back of the screen to the front of the screen. It doesn't matter the direction. But in parallel, what's interesting is if you start at the beginning and you start walking along a wire as if the wire was a maze or a path, you come to a junction. And these junctions in the wires, right, so right here, are indicating to you a parallel network structure. And the idea is you could either go across the left capacitor, or you could go across the right capacitor and finish the path, right? And then there are more complicated arrangements, and these are mixtures of series and parallel, right? So you can see that so if you start at the beginning and you walk, there is a parallel network structure. But then if you, as you walk along the top path, you discover a series structure. And if you walk along the bottom path, it's just a single capacitor, right, on the way to the end. And these are considered mixed. And this actually is not a difficult situation. You might say that the series of C1 and C2 is in parallel with C3. That is, in order to think about this more complicated arrangement, you imagine first recognizing that C1 and C2 is the most basic combination, and you could handle this combination by simply understanding them as being purely in series. So you kind of take the sub-step of imagining a beginning of the path here and understanding this sort of sub-path as a series combination of two capacitors. And then once you understand or resolve this series combination, you can take this series combination and imagine it being in parallel with another capacitor. So it's kind of like, in order to understand this more complicated arrangement, you would first think this way about part of the arrangement, and then think this way about the whole arrangement, in a sense. So you kind of understand the more complicated arrangement as small steps that are the simple, basic arrangements. More than this, like, actually, you can imagine actually the series and the parallel combinations being even more interesting. So the series, you could have a situation where you have, for example, 4 capacitors. They could be the same capacitances or different capacitances in series. And you can imagine that the parallel structure could be more complicated too, where you might say, for example, here is 1, 2, 3, 4 capacitances, all in parallel, like this, right? So, yeah. The whole goal is to look at any particular combination or network of capacitances and be able to imagine the start and the finish as with a single capacitance in between called the equivalent capacitance. And this tends to be the goal of problems that are associated with combining capacitors, is figuring out what's called the equivalent capacitance. Okay, so I'm going to show you how to build up rules in order to be able to calculate this equivalent capacitance, as well as use these rules to be able to say every possible piece of information about a capacitor network. But before I continue doing this, let me say that in my class, during a testing situation or the final exam, I will not make you deal with a capacitor situation that's more complicated than any of these 5 pictures on the screen right now, right? So the truth is capacitor networks, you can imagine in a modern piece of electronics that there's going to be other components. There's going to be diodes and resistors, transistors, really interesting other electronic components, inductors, but there's also going to be capacitors. And depending on what you want to do with your complicated circuit, your capacitor network might be extremely complicated, right? But understanding the capacitor network really does come down to some extremely simple things. So here are some things to have in mind. It's instructive to remember that the basic physical thing of a capacitor is you got 2 pieces of metal of some sort of shapes. In the previous lectures, you saw spherical capacitors and coaxial cylindrical capacitors and parallel plate capacitors. But the idea is I have 2 pieces of metal, and what you're imagining is moving charge from one of the conductors to the other conductor. So if I was to take charge Q from the left side and put it on the right side, what I've taken from the left side leaves me the deficit of the charge. So I have separated charge. And I'd like you to notice very carefully that the net charge of the capacitor is 0. And this is a basic thing about a capacitor. And that's the rule that we're going to use to understand every capacitor in all these possible networks. That the net charge of a single capacitor, like for example, this capacitor here, or this capacitor here, the net charge of those capacitors is going to be 0. The net charge of this capacitor here is going to be 0. And this is going to be very useful for you as a basic rule. Another basic thing to always remember is that a single capacitor is 2 separate conductors. Not one conductor, but a single capacitor, one capacitor is always 2 conductors. And combinations of these capacitors, right? Here's a capacitor in series, the two capacitors in series, right? If you think about it, these are just combinations of conductors. If you think about it, right? Combinations, right? Multiple capacitors is a specific combination of conductors. Let me show you all the conductors in this really simple situation here. So I'm going to change to this green color. I hope people can see it. And I'm going to make the pen really thin so I can draw thin lines. So in this combination of two capacitors in a row, I'd like you to notice that this right here is a conductor, right? It's a wire melted into a, for example, plate of metal, and it's separate from a different conductor. I'll circle it in purple. The different conductor is right here. This is another conductor, right? It's a piece of metal welded to a thin wire, welded to another piece of metal. That is, this is all one conductor. And then I'll use red to outline the third conductor, which is right here, right? So this is really different. Check this out though. Let me see if I can, okay, so this is really interesting to point out. Like, look at this capacitor network over here, this 4 capacitors in parallel, and let's study how many conductors is involved. What's interesting is there's only 2 separate conductors. There is the top conductor, which is completely isolated from the bottom conductor. Can you see that? That is, you can take, for example, I'll draw with this blue. Let me make it skinny again. This blue line does not actually pass through any conducting material, but it does separate the 2 conductors. There's only 2 conductors in this purely parallel network. Likewise, there's only 2 conductors in this purely parallel network, right? You can go and count conductors in this situation as well, right? There is this conductor, right? It's all right here. So that's 1 conductor. And then in a different color, I'll use red. Here is another conductor that is isolated from the others, right? And then here's a third conductor on the right-hand side. So let's make that one in green. So this capacitor network is an arrangement of 3 conductors, similar to up here, but these 2 capacitors are very different, right? These 2 networks of capacitors are extremely different. These 2 capacitor networks each have 2 conductors involved, but they are very different as well. All right? So remembering that combinations of capacitors is just combinations of conductors. So we can have some basic rules that I'll show you how to use in the following video for very specific cases. Charge cannot leave any particular conductor, but it is allowed to move around. This is this free conduction electrons, right, that are in metals. So these free conduction electrons can move around. We will also say, and I've set it up above, that the net charge of every conductor is 0. So what this means is that, for example, let's look at this conductor right here. Let me show you what its shape is, right? I'm kind of like drawing over the red that I was. So this is a conductor. So let's pick this conductor. This conductor right here that's all black is actually part of one capacitor and part of another capacitor. And I want to look at this conductor for a second. It looks like this, right? It's a single piece of metal with a really interesting shape. The shape of this one piece of metal is there's a metal plate on one end that's welded to a really thin wire that's welded to another plate on the other end. So this is one conductor. This is a single conductor. And this single conductor is going to have net charge equal to 0. And that's because this single conductor is surrounded by insulator, and charge cannot pass through the insulator. For example, it might be surrounded by vacuum, and electric charge cannot travel across the vacuum. Okay, so Q net can be 0. So if for some reason the right-hand side plate were to have, for example, 2 microcoulombs of charge, then the left-hand side plate is guaranteed to have negative 2 microcoulombs of charge. That is, whatever the left-hand plate charge is, the right-hand plate needs to be the opposite of it, right? And notice that this is talking about a single conductor, which is different from talking about a single capacitor, right? So you're going to see cases where we consider the net charge of a capacitor being 0. And you're going to, so do you see that this is 2 separate conductors? And we're going to talk about the case where a single conductor is net charge equal to 0. And both of those rules are going to be true at the same time. Because remember that this H-shaped piece of conductor is actually part of 2 separate capacitors. So what we're going to say is that if this is the capacitor C1 and this is the capacitor C2, right? Then that means that if this plate has the charge minus Q, then this plate automatically has the charge Q. And if this plate has the charge Q, which is necessary so that the net charge of this conductor is equal to 0, then this plate has to have this charge, right? So what this means is even if the capacitances are not the same in series, the charge separations in series definitely are the same. And it's got to do with thinking about the net charge. So that's one of the basic rules. You'll see me use it in the next lecture to prove something or to get a particular equation. Here is another basic rule. If 2 conductors are connected by a wire, then they are the same conductor. So here is a metal plate connected by wire to another plate. This is one conductor. And the reason why this is important is a conductor only has one value of potential. That is, if you were to ask, what is the potential difference between this position and this position, right? So this position, right, they're connected by a wire. This is one conductor. You might say that the potential right here has the value V sub A, and the potential right here has the value V sub B. If it is one conductor, that is, they're connected to each other, then there cannot be a difference between the values of the potential. And this is really important. Remember that a conductor is an equipotential volume. And the reason is because the electric field within this conductor, at all the places inside of this conductor, including along the wire and inside of either plate, the electric field is zero inside of conductors. So whenever you ask, what's the potential difference between two places, say B and A, what you have to do is integrate along a path, right, from B to A. So you could imagine integrating along the path that only stays inside of the conductors, and you are only ever going to integrate zero. And this is the potential difference. It's actually A minus B. I put the order wrong, but I mean, if the difference is zero in one direction, the difference is zero in the other direction as well, right? Okay, so these are the basic rules. And now we just have to learn how to use them.